My name's Caskey. I think, who here has seen me talk before about something monitoring related? Good. Okay, so only a few of you will have seen the rants that'll come, and you guys can take small naps during portions of my talk because some of the rants are recycled. I really feel strongly about some things, but I'll try and keep it to a minimum. We're here to talk today about the design of metrics. Numbers dominate operations response. They dominate how we keep track of everything we do. We try and measure as much as possible about everything, right? But too often, in fact, almost the default thing we do is simply take counters exported by something and directly start splatting that onto graphs without really thinking about what is the number that I want to create and synthesize out of those raw pieces of data that is the thing that I'm going to track on a long-term basis. So what we're going to talk about today is essentially about the proactive, conscious creation of specific metrics to achieve specific goals and creating them in a way that allows you to mix and match them that'll be useful for operational response. Okay? So that very vague thing I just said, we'll talk about it for a little while, and at the end we'll have a bunch of questions, and then we'll talk about it again and have some questions, and it'll be a great time. All right? Everyone ready to go? All right. Got one person excited. Okay, so those of you who saw my talk last year or watched the one online where I talked in general about the theory of monitoring, I found this quote, which is from the quote's from 1940, because a bunch of scientists got together in the 30s and said, you know what, we really need an international committee to create what it means to put a number on something, right? And so they formed this international committee, and if you've already read ahead, essentially they said, all right, you got 4 years to figure this out. After 4 years of arguing and bike shedding and going back and forth, the only thing they came up with is they needed more time. So they submitted a report saying, please give us more time. They then spent another 4 years, so 8 years bike shedding. What does it mean to assign a number to something, right? And we're not talking something complex like Euler's number. We're talking about what does it mean when you say there are 4 sheep in the pen? That's the kind of numbers we're talking about here, you know? And how does 4 sheep in pen A and 5 cows in pen B, what kind of relationships can you make between them? All right, I mean, this is the kind of stuff they were arguing about for 8 years. So good news is, solved problem. That's what a metric is. Bad news, it's completely as useless as you'd think it would be after that much argument over something so mundane. So from an operations perspective, a metric consists of 3 key parts, all right? A specific measurement exists in 3 distinct parts. First, it's some named value, right? It's got a name. It has some identity which represents what this sample is. In the case of the example of sheeps in a pen, it's a number of sheep in that particular pen, and the number of sheep in that pen is different than the number of sheep in that pen, and I can count them separately, or I can add them together and have the total number of sheep I have in all my pens, all right? But the identity of the name is not simply sheep. It's sheep qualified by which pen they're in, or maybe it's sheep qualified by which pen they're in and what color they are, all right? A specific measurement of a number exists in a multi-dimensional space. So this is where a lot of your backing stores begin to fall down, is that they try and create a single flat namespace for all of your metrics. And you start doing tricks like packing host names and variable names and maybe regions or availability zones and so on into your metrics, or server type or service type. And you end up with these really complex, messy metric names because you're trying to pack metadata into a single static string. You're going to find out here that you really can't get away with that too much longer. Good news is there are some tools that are beginning to understand that, and that's coming. And then, of course, the value. The actual value is the number, in this case, 4 sheep or 3 sheep or 10 CPUs or 600 bytes transmitted over the network and so on. And finally, it's timestamp. Obviously, we take a measurement at some specific time, right? And that all of these things create individual complications because there are different kinds of numbers. Saying that right now in this room it is 70 degrees, and then a minute later saying it is 71 degrees, doesn't mean I can add the two together and say over the past minute it's been 140 degrees in this room, right? We all agree that, right? However, we can average other kinds of numbers. If I drink 1 glass of water and then a minute later I've now drunk 2 glasses of water, I can say that I can add 1 glass of water and 1 glass of water, and now I have had 2 glasses of water. Right? And it depends on, are you asking me, did I have 1 glass of water in the last minute? I'm sorry, how many glasses of water I have in the last minute? Or how many glasses of water have I had since I got here? All right? So when we're actually gathering these individual pieces of data, there are 3 key three key variables that we have active control over when designing our monitoring system and deciding what we're going to gather. Obviously, once we've created some metric, whether it's number of sheep, number of CPU seconds executed by a process named foo on this particular machine, we have three things that we need to decide upon. How quickly are we going to be scraping that data? Do we care about how that changes on a second-by-second basis, or do we only care how it changes on an hourly basis or a daily basis? For myself, I tend to be okay measuring disk space on the span of hours. However, CPU activity, I often need something much more fine-grained on the order of minutes. Also, latency. How old of a reading is useful? Knowing about a 20-second CPU spike that occurred last Tuesday is really not that useful, right? However, knowing that disk space consumption has increased by 10% per day over the past week, and I'm going to run out in another 3 weeks, that's useful. But I don't need that data on a continuous basis. Additionally, diversity. How many different kinds of metrics? If you have 1,000 servers, each of which has the same metric on it, you have 1,000 different data points, right? Now you can say, I'm just going to add up my total disk usage across my entire fleet and keep one number, or you might be tracking disk usage on a per host basis. You might be tracking CPU usage not on a per machine basis, but on a per process basis. You might say, you know what, I don't care about the difference between kernel time, wait time, and system time. All I care about is busy time versus idle time. Right? You have control over how you're pre-aggregating these elements, because very often the counters that we have are very, very precise. And in fact, the latest version of like procmem, there's quite a bit of additional detail about what the memory looks like. Not the latest, but it's much different than it was 5 years ago, where it was just free cached and buffers and in use. So you have control over how you're gathering those, and that determines what kind of data load you're dealing with. So those three things and how you pick them is determined by what kind of goal you're trying to accomplish with your monitoring system. This here is from my framework on monitoring, and these are the four major categories of why you'd gather data, labeled with how difficult or easy the resolution, latency, and diversity values are. Operational response requires high resolution. We've got to gather the data frequently so we know when something's going wrong. It requires low latency, which is confusing because I use the L plus here, because the plus means it's the hard case in latency, not the big case in latency. And D plus because we usually want to know which machine in our fleet is melting down, not some machine in our fleet is melting down, right? And then as we pair back on each of those individual values, we get to lighter and lighter versions of data. And very often, we can construct those simpler versions of data from the more complex operational health response data. Or sometimes, like for instance, in the case of product management, you have other data sources that you don't use at all for operational response, but they're batch jobs that run hourly or daily to get information like 7-day actives and various product response things. And then graphs are examples of the kinds of things. Obviously, the top one's got anomalies that are occurring. The middle one's showing something like intraday latency distributions. The third one is obviously there's resource consumption is going through the roof. And the bottom one looks like it's broken down by market. I think that I cribbed that from Windows Phone market share by country. But you get the idea. Turns out in Italy, they're like going like gangbusters. I totally didn't expect that. I was just looking at random graphs and I thought, oh, this one looks interesting because there's clearly one area that's going crazy. And in Italy, the Windows Phone is very popular. So, where's my next slide? There we go. So operational health and response. This is what I'm pretty sure just about everybody here cares about, right? If you hear about product quality metrics and market development, you're at the wrong conference. And hopefully, on the last day of the conference, you figured that out, by now. I used to teach at university, and I still do part-time. And, the kid who on the third week realizes they are in the wrong classroom. Yeah. Anyway, so, yeah. So what are operational health response? It's basically any of that data that you need to solve a problem, right? It's also, as I said, it's the hardest case because we want the data that's the most freshest, the most detailed, because we want to be able to slice and dice it to find exactly which spindle on which machine has too long of an I/O wait queue, and so we can go about kicking it, shedding load, doing whatever we need to do to make that thing happen. Find out that it's got a flaky controller that's timing out, do whatever we need to do. Until we can find that specific piece of information, where basically all we see is a blinking red light that says something's wrong. You know? One of the best things about Star Trek, all the versions of Star Trek, is when red alert occurs, pulsing red lights come on. And there's nothing more useless than a pulsing red light when everything's hitting the fan, right? So pulsing red lights are bad. A specific graph that says, by the way, spindle 7 of machine 12 in rack Q3 is on fire. So what kinds of things can go wrong? It turns out that there's a fairly limited domain of things that fail, but unfortunately that domain is very, very broad in each of those concepts. Like, you know, bad code covers everything from memory leaks to infinite loops to poorly written code, which consumes too much resources on some code paths. If you've ever had a situation where, okay, query A, B, and C for this particular web app uses, say on average, a millisecond and a half or 3 milliseconds of CPU time, but query D consumes 900 milliseconds of CPU time. It can be very difficult to balance your usage across machines unless you have some way of controlling at the sub-request level. Obviously, bad hardware happens, bad data. Bad configuration is kind of included in bad data, but bad configuration also includes operator error, fat fingering your update, and so on. But bad data could be corruption on disk, bit rot occurs. The more servers you have, the more bits that are out there that could be flipped, and that's always a bad thing. And you know, some nasty combination of all of the above, for instance, hardware that silently, you have multiple hardware failures where one of them's flipping bits one way, the other one's flipping bits the other way, and the combined effect causes the CRC32 check to succeed, or math errors in your CRC execution code due to a bug in the CPU. I mean, or not a bug, but a flaw in the CPU. I mean, all these things can and do happen. And of course, something else entirely that is not even really categorizable under these things. And that's where things like, you know, hunters shooting your fiber connection points on power poles because it's a bad hunting season and they're out in the middle of the woods and fiber runs through the middle of the woods. Or a rat crawling through your power distribution center and arcing lines and bringing down everything at a place where you didn't know you were a single point of failure because you figured all it is a bunch of copper going from here to about 6 feet over there, and how could it fail? Turns out charred rat can do a lot of things. Actually, I say that, but in our experience, the rats tend to do pretty fine. About the minimum length for like a 40,000 watt PDU or so is about cat length. Yeah, I know. Yeah. Yeah. Thank you for the sound effects. So yeah, and then of course, those who don't know, the great heron has a wingspan of 7 feet. It can, all right? So fun stuff. Anyway, so all sorts of stuff fails. But so where do we get the data that we're going to use to solve this problem, right? There is lots of data available, and I apologize for the tiny font. You really don't need to know what it is, other than it's a whole bunch of numbers that are written up and that aren't very interesting because they're just dumps of procmem info, some SNMP network interface card data, and looks like CPU time. There's going to be several slides that have tiny font. Well, as soon as I get the approval, I'll be sharing the slides with USENIX, and you'll be able to view them on your own. But really the details in these numbers, not the important part of the talk. It's what we're going to do with them. It's the fact that these numbers as they exist are not very useful, and we're going to try and make them useful. So we get data from lots of places, but in the end, we're essentially saying, I'm going to read some value, or 4 or 5 values, and I'm going to see how things are now compared to a minute ago, 5 minutes ago, a week ago, last week. You know, you're going to compare it to some time period to say, is this normal or is this not? Sometimes normal hasn't changed much from a minute ago. Sometimes normal is the same as it was last Wednesday at the same time, right? Of course, it's easy to say that. There's a lot of work that goes into doing those 2 steps. Metrics. So metrics can be combined in interesting ways. And one of the problems with, I'm going to flip back real quick, with these different presentations is that often the native way we get access to these numbers conflates things like temperatures, which are a particular type of interval scale, and disk space in use, which is another type, or things like, in this case, the very first item in proc mem info is mem total followed by mem free, and then a whole bunch of other things which sub up to subsums of other elements in there. So it's not a single flat set of values, which if you add them all up together, you get your total amount of memory. It's the same the same bytes are represented multiple times in this list of numbers, right? And that can cause confusion later on. And it's all about eliminating confusion, providing clarity, so that when you look at that dashboard and you see a stacked graph with your memory utilization and one of those bands has expanded, you know that it's not because I'm counting bytes that are in other bands or something else. It's that band is going wrong. So we can do lots of different things with numbers. These are the implicit intuitive things that all of you guys know. Obviously, if I have a machine with 12 gigs of RAM and after I start something up, it's using 10 gigs of RAM, and on a different machine which had 8 gigs of RAM free, and after starting something up, it's using 6 gigs of RAM, probably 2 gigs of RAM consumed on both of them in the same process run on a machine with, say, 32 gigs of RAM will have 30 gigs of RAM left over, right? That's because you can compare equivalents of differences between quantities of RAM or disk space and so on. But a hard drive with 20 gigabytes free that is only a 500 gigabyte hard drive is fundamentally different than a hard drive with 20 gigabytes free that is a 10 terabyte array. Right? Nobody wants to have only 20 gigabytes free on a 10 terabyte array, because it's a very different situation. But if you have 20 gigabytes free on a VM that's only got 500 gigabytes and it's got static disk utilization, you really don't care. However, I have other machines where if I only had 20 gigabytes free, I have machines that if I had only 1 terabyte free, I'd be freaking out because the total size and relation is important. And that's about the equivalence of ratios. 75% utilization is 75% utilization. You can compare that whether it's a 10 terabyte array or a 500 gig drive. And being at 99% utilization on either of them is bad, even though the absolute amount of disk free is entirely different. And finally, combining. This is the best part about metrics, and this is the part where things begin to explode. Metrics are like Voltron, right? The more you hook up, the better it gets. All right? So it's only when we combine our metrics that we're able to get useful insights. Very few of us look at a dashboard with one graph with one line on it, because it's not that one number in isolation that we care about. It's what the numbers in combination with others occurring at the same time on different components and how they're moving. You know, how is disk space related to I/O? How is memory consumption related to the number of incoming queries that we're receiving, and so on and so forth. It's the combination of metrics that makes it interesting. However, flat namespaces, to bring it back to the naming of metrics, make it very difficult to combine metrics in useful and dynamic ways. So these are the implicit properties of numbers. Now to get to the exciting statistics and numerical theory part of the talk. There are 4 explicit conventions and meanings when it comes to numbers, all right? We'll try and go fairly quick through this. The important thing is just be able to pull up, know that this exists, and if you are ending up having difficulty computing some value, know that maybe you should go and get this list and look at the types of each of the things you're trying to combine and make sure that you aren't inadvertently doing something like dividing disk utilization by NYSE index for the last 3 days, right? I mean, you could end up with different kinds of numbers that are either comparable or not comparable. So nominal. Essentially, this is categorical. I'm going to go in detail about each of these in a moment. Ordinal is, you can do everything with an ordinal number that you can do with a nominal number. These all build on each other, except you also get an ordering. You can compare them to each other. Interval numbers are when all of a sudden the differences between things, just because A comes before B doesn't necessarily mean something until the distance between A and B has some implicit value. The letter A and the letter B are 1 letter apart, and the letter B and the letter C are 1 letter apart in the alphabet. So I can actually say, if I add up the difference between A and B and C, I get 2 letters apart, and that's the number of letters between A and D. I'm sorry, A and C. And that's the kind of thing you can do with an interval scale where you've got equality of spacing, or not, and that doesn't mean that every value is equally spaced. That just means the spaces between the absolute values has inherent meaning. Okay. And finally, ratio scales. This is where you can you're then correlating things. Essentially, they come about when you combine multiple interval scales and you divide one by another. All right, number of bytes free divided by the total number of bytes on the disk. that's a ratio, and that's where you can then compare ratios to ratios by saying 99% utilization on this disk drive is probably as bad or similarly bad as 99% utilization on this other drive, even though the actual values are wildly different. So nominal numbers. With nominal numbers, these are where you are applying a label to something just completely arbitrarily. All right? Now these come up in things like when we're categorizing CPU execution state. If I say 12 milliseconds of CPU time has been consumed in kernel mode, the fact that it's in kernel mode is an example of a nominal label. Whether it's kernel mode or user mode or wait time, I can't subtract the difference between a wait time and I'm not talking about the value of wait time. I'm talking about the fact that I've labeled wait time state 2 and kernel time state 3. I can't subtract those two and get anything meaningful about the difference between them. Right? So if I take 42 and assign it the value of the meaning of life, all I know for sure is that 13 is not the meaning of life. All right? I can't say that 13 is less than the meaning of life, but I can say 13 is less than 42, but then I'm talking about the number 42, not when I'm using 42 to represent the category of meaning of life. If you use SNMP metrics, you'll discover that they use numeric enumerations for lots of different states, like up versus admin state up, admin state down, and so on. And this is an example of something being in state 1 versus state 2. You can't add, or you can't sum up the value of all of your states and then divide it by pi and get something useful. Categorical or identity. This is where does more than one thing have the exact same label. Obviously, CPU mode while executing code is a categorical state. I can have multiple CPU seconds that have the exact same kernel mode. However, I can't have more than one machine that has a particular name. That's a singleton. It's unique. Okay. And finally, when I'm trying to gather statistics out of these metrics, there are only 2 that we use and 3 general statistics that you can do. Ignore the ones that are in parentheses. Those are there so that somebody who is a polymath doesn't say, but what about the Riemann coefficient and stuff? But the fact is that taking the mode, what is the most common thing? Am I spending more of my time, CPU time, in wait time or in user space or in idle time? Being able to just categorize what's the most common element, and of course, the iterated version of that, what does the distribution of my CPU utilization look like, right? A stacked line chart is the most common way we render these sorts of things. Ordinal numbers, building on top of that, ordinal numbers, all right, I'm going to speed up a bit because these are really boring things, but ordinal numbers is where we then take some value and we create an implicit ordering of them, even though the values might not have the differences might not have meaning. Coming in 42nd in the New York Marathon means that you definitely finished behind the person who came in 24th, but there could be an hour's difference in there, right? And an hour difference is pretty meaningful in a marathon, right? Being the second largest consumer of CPU on your server does not necessarily mean it's something that should be killed to free up resources for the first biggest user of resources, because one may be using 99.9% of the CPU and the other one's using 0.1, right? So ordinal numbers have very specific uses, and you don't want to create a blanket rule like, oh, always kill the second biggest memory consumer on a machine if you're running out of memory, because the second biggest might be very, very, very small. Similarly, version numbers. Version numbers, there are all sorts of wacky rules for creating stable orderings over version numbers, right? And I like this example because here I have version 217B-1 and version 158R4. And under the very naive rule of just looking at the first leading component, 2 is bigger than 1. I don't need to look at the rest of it, and I'll leave it at that, right? However, would it be meaningful to subtract one version from the other to get the distance between the two? In this case, there's no way of knowing how many releases there were between those 2 versions. In fact, under the naming system, it's designed to allow an infinite number of releases because at any given point in time, there may be more or fewer maintenance and security releases of earlier versions, right? But we can at any point in time always say this one comes before that one and then do something meaningful with it. Host name, this is a little bit different. If you have a structured naming system, it might be meaningful. In this case, these 2 host names are 20 EB. They're like 30 rows apart, no, 30 racks apart in different rows, and one machine is 12 slots lower in the rack than the other one. Useful if you're trying to find what machine has the hard drive that's failed in a giant data center, right? And so having something being able to say, okay, if I'm looking at the rack that has AGDQ11, no, the one that the ADGQ, I'm sorry, the ADG something 11 that I want is one rack to the right. So being able to navigate by that can be helpful, but that's often implicit in the type of the data that we're using. But you certainly wouldn't average which row one server's in with another server row. So, and of course, the valid statistics you can get now are obviously the same ones before, the mode, but also the median and the percentile, and of course, the Spearman coefficient and the Kendall and all that stuff. But you don't need to worry about that. He's a statistician. My condolences. Anyway, unless you're getting into dynamic autocorrelation and machine learning with respect to fault finding across disparate sets of data, then you don't really need to worry about those coefficients of correlation and so on. If you are and you do, then more power to you, and I look forward to, using your software as you're carted off to the insane asylum. So interval numbers, again, this is what we implicitly think of as an absolute count of something, the number of terabytes you have of disk, the number of CPU seconds you've consumed. The difference between 1 CPU second and 2 CPU seconds is exactly 1 CPU second. And if I add two CPU seconds together, I get 2 CPU seconds, right? However, even though something is an interval, addition is not always valid because I can't add 70 degrees and 71 degrees together and say it's 141 degrees in this room, right? So you can take the mean, standard deviation, as well as a couple of other correlations and regressions. And finally, ratio numbers. This is where we do a lot of our work because we care about how things are changing over time, and specifically one number changing in relation to another. And if you're going to track one number changing in relation to another, it's almost always 2 interval numbers that are moving in concert or in disconcert that you care about. Now, specifically, I talked about temperature and versus CPU seconds and so on. This gets into the notion of gauges versus counters and does summation matter, okay? Now, gauges naively are simply an absolute measure at a specific point in time like temperature or the current number of bytes per second going out through a particular network interface. Gauges are often not as useful as counters. If you have some gauge value that has a raw counter available underneath it, never use the gauge counter, right? If somebody's offering up, oh, system load, don't care about system load. Count how many CPU seconds have been consumed since the system booted, subtract it from the last time you checked, and look at how long it's been between those 2 measurements, and you'll always get a better, more useful value, right? You don't want to just say, I'm going to average the CPU load or the percentage busy over the past hour that I got from the system checking every 5 minutes, because that's going to hide a lot of details. So some have meaningful 0 points. This is important. Having 0 CPU seconds is a meaningful value, and if I were to add 0, 0, and 10 together, and I get 10, I'd know that I'd use 10 CPU seconds across 3 cores or something meaningful. However, adding 0 degrees, 0 degrees, and 10 degrees together does not mean my average drive temperature is 3 degrees. Well, actually, it does mean that, but that was a bad example. Yeah, because temperature is an interval number, and the mean value is an always valid statistical abstraction of an interval number, right? So bad example, don't care about that. But summation, being able to sum your metrics across subsets of the dimensions that you've got them in is useful. Being able to say, you know what, yes, I'm tracking the number of sheep that are in all of my pens, and I've labeled all my pens. Summing across all of them irrespective of pen gives me a useful number. Summing by color irrespective of pen gives me useful information, right? So, but of course, summing by drive temperature across all drives doesn't really tell me that much useful. Or the kind of thing I want to know, like my data center's on fire, could be gotten by a slightly more direct measurement than the sum of the drive temperature of all my drives. There's a great story about that we'll talk about afterward. It's a fun anecdote. Actual metrics. What kind of things are we actually caring about? 3 basic ones: memory, network I/O, and CPU utilization. Everyone knows these. They love them or hate them. and you want to track them. Now, I'm going to go with a very simple model of I just care about the host level resource. Assume you are the manager of a VM or a cloud environment. You aren't too concerned about what's going on inside each of your VM guests, but you are concerned about overall your fleet, what the total utilization is on each of your nodes for migration and load balancing and packing and so on. So this example is going to talk about individual hosts. So just looking at memory, here are two different data sources for memory. This is the SNMP dump of memory info, the proc mem info dump of memory info. There's lots of numbers. We don't really care about them because only a very naive dashboard would simply take all of these values, name them, save them, and put them on a dashboard. Because it's not created with intent. It's just, here are the counters that happen to be useful. On the case on the right, here are the counters that happen to be useful for someone who is implementing a memory manager, and they need to keep track of these specific values. In the case of the ones on the left, here are the ones that an international group decided was a useful set of metrics to get gather on any arbitrary computing device that may be connected to a network, right? And they're so generic as to be almost useless. So, oh, and of course, what is a metric? It has a name, a value, and a timestamp. Anyone know, can anyone tell me what the two hardest problems in computer science are? What? No, not time. Naming.
Caching validation and off by one error.
Yeah, I like to call it naming, concurrency, and off by one errors. Those are the two hardest problems in computer science. And yeah, it's funnier when you do it in print and you actually make the words interleave. But anyway, yeah, I'm giving you guys some really bad jokes. I mean, don't laugh at me. You're just encouraging me. Yeah. So the value and the timestamp are attributed some number, right? We're going to have to put some thought into which value we're tracking. I can tell you now, it's not going to be mem total. That's never a metric that you'd want to bother recording because it's really just the sum of all the memory that's in other states, right? So what do we call this metric name, right? What do we want to name the value that we're tracking memory with, all right? It's going to start with memory, right? Like right now, the amount of memory in this machine that I pulled the example from is 64 gigs, right? That just happens to be the amount of memory that's on that machine. However, if all I could tell you about my fleet was there's 64 gigs of memory, that'd be very unuseful because until someone racks up more hardware, it's always going to be 64 gigs of RAM, right? That number's not going to change. So we need to create disjoint dimensions to subdivide this single value into a number of different time series that when we sum together, we can see that, yes, indeed, the total amount of memory in the fleet is 64 gigs, but what are those 64 gigs doing at any particular point in time? Obviously, a very good starting place is to say, you know what, I care about the memory on this machine versus that machine. Now, in this case, my original number was from just one machine, but imagine I said it's 128 gigs at the beginning. As soon as I pick a host name, now I know that there's 64 gigs on that host, all right? Now, this label is an example of an open-ended, unbounded, distinct identity dimension, right? There will never be more than one machine unless you've really screwed up your host naming and your DNS is broken and you're having a separate problem that day than your metric design. There is only one machine with the identity AACD12. There's one machine, it's AACD12. It's going to be AACD12 today, it's going to be AACD12 tomorrow. It's going to remain AACD12 until it's decommissioned and maybe a new piece of iron comes in to replace it, at which point it might have a different amount of base memory, right? Or it gets upgraded in some way. So it's unbounded, open-ended, and distinct. All right, but let's say what I'm actually trying to look at is how much memory is available, right? So now I'm splitting this even further. I've taken that 64 gigs, and I've broken out just one aspect of it, specifically the mode of the memory. In this case, it's free memory on that machine, right? And I've got about 45 gigs, 44 gigs of free memory on hostname AACD12, right? Now, I've added an example of a closed set of fixed values. There are only so many different states that memory can be in. Free, God, sorry, they created a bunch of new names for them. Free, in the old style, free buffers, cached, and in use. But now there's active anonymous, active disk, inactive disk. And what was the third one? Yeah, off by 1 errors, yeah. An active off by 1. So now I'm actually pulling out a particular aspect of free memory on that machine. Now, if I were to just name my metric this, I would have, okay, I could track free memory across each of the individual machines in my fleet, and I'd have a different instance of this metric for every single machine in my fleet, and a different instance for every machine in each mode, right? Because while I'm using kind of variable notation here, the entire thing with its bound values makes up the name of that metric. It's memory with this host name in this status as of this timestamp has this value, and that's one metric sample. Now, of course, free memory could be telling me about the swap space on disk, and in fact, depending upon whether you're using the SNMP interface or you're using the proc meminfo interface, if you look at just the free memory value, you may or may not be including paging files, swap disks, right? Now, obviously having 64 gigs of swap available and 0 bytes of real memory available is a very different situation than having 64 gigs of real memory available and 0 bytes of swap available, right? But if you just naively take one of those dumps and graph it, you are going to be looking at one or the other. And unless you were the person who set up your monitoring system, just looking at a dashboard, you don't know if the person who created it actually differentiated between those two classes of memory. Hopefully they did, right? But usually we pawn this off onto some junior admin to go and update monitoring and figure out how badly could they do it. Well, they can do it, and they can do things that'll be misleading when it comes time to figure out why is everything going wrong. So we add another dimension to the namespace, and we end up with a simple 3-dimensional namespace, which is what host is the byte on, is it a free byte, what state is that byte in, and is that byte a real byte of physical RAM, or is it a virtual byte on a disk somewhere, okay? And this completely sums up one way of tracking memory for someone who's trying to solve a very specific problem. They're a VM cloud administrator who wants to track the available memory on their fleet in a meaningful way. Now, they wouldn't have just that one value, right? They would have, their metrics would actually end up looking like this. And here we've got, the host name is the same on all of these, but instead of just free memory versus total memory, what they're actually tracking is the number of active bytes, number of inactive bytes, active anonymous bytes, inactive anonymous bytes, active file bytes, inactive file bytes, number of free bytes, number of shared bytes, number of buffers, and then the very last element changes to true because now we're looking at the non-physical RAM values, and we've got free and used. Now, there's also some divisions within that, but I ran out of room and I didn't want to actually enumerate every single thing. So what can we do with that? Now, because we are now tracking a dozen or so individual streams that total together to our actual memory, we can run queries over it that aggregate those into useful values. In the first case here, I'm using a pigeon notation. Can everyone see this, or do I need to make it bigger? Bigger? OK, yeah. Figured I would. No, not change page. Let's just do it this way. All right. No, I don't want to print my presentation. I want to present my presentation. Yeah, I didn't realize that the projection would be 1024 by 768. All right. There we are. So let's see. Wow. So I have to zoom my interface out to make the thumbnail smaller so I can take this and make this bigger. That's intuitive. How about that? Can you see that better? I'll go and put it back into presentation mode. Well, that doesn't work. All right, we'll try that and see what happens. All right, can you see that better? Yeah? OK. All right, so what we're doing is we are summing our memory metric, in this case with a specific value of AACD12, the host name. And I'm using state equals star to mean I don't care what the state is. If you're familiar with SQL statement, this would be similar to an SQL select where host name equals this, where physical equals false, group by host name and physical state, and get an aggregate value, right? And so this first query would yield a value which is total memory with the label, host name label still present, no meaningful state value because it's really all states, right? As well as being false for the is swap value, right? Similarly, if I do the same query but where I say state is not equal to free, this will give me the bytes in use. So now I have the bytes in use and the total number of bytes, and I can divide them out, and I get the percentage of the memory load. And I've also converted that interval value into a ratio value, right? Your monitoring system needs to be able to store and manipulate metrics in this manner for you to create meaningful dashboards, all right? The inability to succinctly express this is the source of a huge amount of frustration with people trying to create dashboards, trying to create monitoring systems, because they can't simply say, you know what, I want to sum all my free memory, free real memory, across all of my fleet, or I want to look at how free memories change over time, or I want to look at how locked pages is changing over time, and then you know what, now that I see that locked pages is what's changing, I now want to break that down by host to see which particular host is seeing the growth in locked pages. Is this something that's occurring across every one of the machines, or is there one or two machines that are experiencing a difference in locked pages? Being able to explore your data until you eventually find out that on this particular machine, that particular kind of memory mode is changing in this particular way is what allows you to drive your incident response directly to the source of the problem. Now, without this, if you're just gathering very broad spectrum data, without SSHing into individual machines and checking what those counters look like, you can't just from a dashboard drill down and find that solution. And so by tracking each of the individual components of the metric labeled by what particular place it resides in that multidimensional space of your metrics, and then selectively summing across dimensions, you get the ability to do operational response purely from your dashboards. And at this point, without even having to leave your dashboard, you can say, you know what, I know the problem's on this host, and it involves memory. Whoa, that was loud. Okay? So, similarly, these same kinds of a process would be used for something like CPU utilization, except in CPU utilization, we don't worry about page files. We care about which core is in use and what state the CPU time is being consumed in, all right? So what changes are the labels that differentiate what quantity of CPU seconds we're consuming. Follow? Any nods? Yes? No? Okay. So the amount of user mode time consumed by CPU 3 on host 12 is its own meaningful metric. And how that changes over time is useful. Most of the time, unless I'm trying to figure out something specific that's going wrong, I'm going to sum across all the CPUs on a machine because I care about the total machine health. If I'm dealing with that, unless, of course, I'm dealing with VMs, or I've perhaps bound VMs to specific physical processors, right? And being able to compare this subset of CPUs against that subset of CPUs can be meaningful. Knowing that a 12-core machine is pegged at 33% utilization isn't interesting unless you happen to know that running on it is a pinned 4-CPU VM that's at 100% utilization on all its cores and 2 completely idle VMs. Or it could be 4 3-CPU VMs that are all pinned to CPUs, each of which is happily consuming 1 CPU, right? Until you can subdivide the data by that information, you aren't necessarily able to figure out whether something is even a problem or not a problem. So network I/O, this changes the subset of labels that you'd be using because instead, you'd be looking at the host name, which particular physical interface or virtual interface it's occurring on. In this case, you would have multiple virtual interfaces which may be overlapping because you might have the single bare metal interface, which has its own set of counters, and then you've got virtual interfaces on top of that, or bridge interfaces and so on, each of which are counting their own metrics. And you'd be looking at the bridged version or the VLAN version of an interface and comparing that to the overall one. For instance, you might be experiencing really high packet loss on a virtual network interface that is only at, say, 10% of its utilization, but when you look at the bare metal interface that's underlying and backing that one, it may be at 100% utilization because of other interfaces that are, other virtual interfaces that are bound to it. And so being able to, in your dashboard, without having to go and log into machines and look at counters and manually add things up and cut and paste things into your calculator, being able to directly drill down and select which subsets of these metrics you're counting is very, very important. Of course, the really hard part here is getting your storage layer to play along, right? Very few storage layers can handle arbitrary labels on your time series. All right. Good news is OpenTSDB does. I'm sure there are others that are coming because in order to do operational response on large fleets, you need to delay as long as possible the time that you're finally SSHing in or dispatching a hardware operations guy to address a hardware fault. You need to be sure that you're going right to the right solution. You can't be saying, all right, I know it's one of this group over here. I'm just going to connect to each one of them in turn and see which one is likely to be doing it. You need from your dashboard to be able to say exactly where the problem is. And unless you have a time series that you can look at, that eventually, by stripping away the summation in combination with other elements, eventually only uniquely identifies a single thing, either a spindle on a machine or a network interface card or a switch port and a switch, you won't be able to direct your on-call response from your dashboards. And the goal here is to make it so that you start at your dashboard, you see something wrong, you drill down into your values, and you've diagnosed the problem without having to play, let's go see what's going on, right? So, because simply walking around the data center sniffing for smoke is not the ideal way to find out what's going wrong in your service. So, of course, this has all been in the context of you're a cloud manager who only cares about things at the aggregate host level. Many of us are application administrators who are responsible for specific services running on those hosts. And while it is useful to know that the host's total CPU utilization is below some threshold, if I know that I've deployed an app on a 12-core machine and it's consuming only 10 cores consistently, then I don't need to really worry about exactly what the headroom is there in the free CPU space. I'm fine. However, if all of a sudden I know I'm on a 12-core machine and my app is using 11.9 cores of CPU time across all modes, then I know that there's going to be a problem. And so we tend to think of CPU utilization, disk I/O, network I/O, and memory utilization on a per process basis. And then on a secondary level, we know that there's a machine under there which can also be exhausted of resources, but that's a second-order problem. Knowing that a machine has exhausted its resources and needs to be rebalanced by shedding load and shifting it or live migrating it to another machine is one kind of on-call response. Knowing that an application is exceeding its defined boundaries of allowed utilization is an application on-call response. Okay? So the way you do that is you'd simply change what the set of labels are that you're applying to these values. And so when you're scraping these values, sometimes you'd be applying just the host name because that's all you care about. Other times you're like, you know what? I want to be looking at not only the host name, but also the value of argv0 and the process ID, because I want to be able to sum across all processes named HTTPD, right? Or if you're a Windows administrator, all processes named SVC host. Right? Now, this is one place where Windows has a slight edge over Linux in that they differentiate between argv0 and the name of the process. But it's a very slight edge because almost nobody names their process. It's always just foo.exe. In the past month or so, I've been having to do a lot of WMI. Who here deals with WMI in Windows administration? All right, yeah. Okay, so I did the rest of you a favor by not adding WMI examples into this, but the same thing applies to WMI. Your WQL statements are going to get out values. The objects that you get out, they contain very weird combinations of values that you need to then extract and pull out. You take those name values, combine it together, and so on. So, all right, back to the rest of you guys. In the case of, so in the general case, we care about host name and process ID and the process name itself, because if the process restarts as a different process ID, we probably don't care about the individual process ID because we'd usually be summing across all process IDs. But if, for instance, it's a multi-threaded program and one particular thread's becoming wedged, knowing that on this machine where there's 40 or 50 processes named the same because they're all different threads of the same app, and only one of them is running at 100% CPU utilization, that's a useful thing. And you can then say, you know what, there's one wonky thread on that machine. The problem is something probably related to query dispatch, and that further guides your response and where you're going to file the bug and what you're going to do to remedy the issue. And finally, for CPUs utilization, we probably don't care about what was the thing? We want to keep the process ID stuff, but we care about the core and the state that it's in. I'm sorry, we care about the state that it's in, not necessarily which core it's running on. Now that may differ, but if we're using CPU and we're tracking it by host name, process ID, and state, an individual process thread can only be running on one core at a time. We really don't care if it's bouncing around among cores, unless we do. This comes into thinking about what kind of failure modes you're trying to look for. If a thread spending too much time moving among your cores is an issue that you care about, then you do want to be able to examine how often a thread moves from one core to the next, right? And some people only care about cores in the abstract. Others care about, does this core share the same die as another core? You've got which socket is that core in and which core is it within that socket. Some people care about that. You'd add labels to provide that information as well. So you aggressively label your individual time series to the maximum granular detail you'll need for your operational response, and then your dashboards can lead you directly to the problem at hand. So, yeah, what I just said. So when you design your dashboards and when you gather your metrics, don't just say, you know what, I'm going to slurp in everything in procmem info and turn it into a named variable. Think about, what value do you want? Do I care about the memory utilization of this host? Do I care about the memory utilization of this service? Craft your metrics to address the exact information that you're trying to gather and pull out. Start with that list of ways that things can fail. Comment? Sorry, I thought I heard something. Start with that list of different ways things can fail. How will you identify different hardware failures within your platform? What kind of hardware failures are you concerned about that won't be detected by other means? And then let's go craft a set of metrics. Maybe you just don't care about disk I/O, right? It may be that disk I/O is interesting, but it's so unlikely to be relevant to your app because you do everything in RAM and you've got a pittance of disk space that you use. As long as the host has enough free disk space, you really don't care about the bytes per second that are being written out on a per disk channel basis. Some people do care about that stuff. You're going to overgather metrics. And this is something that people don't always realize. The metrics that you're gathering for host health aren't necessarily the same metrics you're gathering for application health. Sometimes those are different teams, right? Sometimes it's team 1 is responsible for the host's existence, and team 2 is responsible for the application that lives on that host, all right? So those two teams need to have a way of coordinating their data collection. If they're very lucky, they can use one system to collect the data that's shared by both. The reality is that most times you end up with each team independently collecting the data that's relevant to them in the format and structure and labeled in a way that's useful for their on-call response. Now, if there's one on-call response team, there could be only one interesting set of data, but even if it's only one team, depending upon what playbook you're running, a hardware failure playbook entry might be interested in drilling down by one set of values, and an application response playbook entry would be interested in looking at different sets of values. Existing metric names are terrible. Your data store is going to be a problem. If your current metric data store uses a flat namespace, start shopping now. Start looking around. Start contributing to open source that creates underlying data stores that don't have flat namespaces. We as an industry only have one open source time series database that's generally available that has arbitrary labels that I know of, right? And that's OpenTSDB, and we need more. We need more because we have to be able to track metrics at a very fine-grained level in order to do operational response across thousands of machines. And every one of us, if we count up how many VMs we're managing today and look at how many bare metal machines we were managing 2 years ago, 3 years ago, the number of hosts, the number of instances of hosts that we have is growing and growing and growing. Who here has gone to containerization? Okay, who's dabbled with containerization and is looking at it, and who is like fully containerized, everything they have runs in a container? Okay, a couple people. These people are leading the way because now what was one machine with a couple things running on it, which was The old way we had one piece of iron that ran 2 or 3 different services. Then we went to VMs, we're running one service. With containerization, individual services are now being divided up into pseudo virtual machines, each of which has its own stream of metrics. And the on-call response needs to be able to figure out which of these containers is of interest, right? And so you're going to keep getting more and more and more data points in this high-dimensional data space. Instead of just being host name, process name, process ID, it's going to be host name, container name, or just container name, right? Host name may not have enough variety, or container name and host name because you're live migrating containers among hosts, and it turns out that this container on that host has some odd interference with the particular revision of the CPU architecture. And you would only find that out if you knew that only every time that container got live migrated to that particular machine in that rack, was that machine having a problem. All right? Now, these aren't hypothetical things I'm describing. These are actual incidents that we've encountered. These happen, and without the data to figure it out, it drastically stretches out your on-call response and the time to remediation. So, and try to think multidimensionally, right? We are no longer single-dimensional beings. That time is long since gone. So think multidimensionally. All metrics live in multiple dimensions. That brings us to the end of the main part of the talk. We got lots of time for questions and chit-chat and clarifications. There's a microphone there if you want to ask a question for the benefit of the recording, or I'll repeat what you have to ask. Thoughts? Are we all multidimensional hypermetric gatherers? All right, one of us is. The rest of you guys are dinosaurs. No. Rawr. Yeah, he's a dinosaur. So, anything? I know I gave you a lot of stuff, kind of like, but stew over it, think about it. Who here is gathering labeled multidimensional metrics already? Somebody's got to be. Yeah, we got 1, 2, 3, 4, 5. So people are already doing this. Who, of those of you who are doing it now, would you want to go back to a flat file namespace for your metrics? I see a no, I see a no, I see a hell no. Yeah, it's because you can only move forward with this stuff, and there's no way of going back to a flat namespace. Who here is packing metadata into metric labels about what host it came from and what particular type it is? 1, 2, 3. Okay, surprised. How are those of you who are not using labeled data and not using, hopefully you're using some monitoring. Who here has no monitoring whatsoever and there's like, it's gonna, yeah, all right. May the force be with you.
Write once, read never.
Write once, read never, yeah. No, I like that kind of data.
Use randomly generated.
I just dump it in dev null. Cat proc random, pipe dev null. Yeah. Any thoughts? Who thinks I'm full of shit? And why? Because I want to know. There are multiple errors in what I just said and multiple fallacies. I'm sure, just because I've never gotten it right. The first time, second time, third time.
I was wondering, do you guys have some kind of integration between your log, like event data that is not necessarily in a interval time series database? Or maybe I missed something, like maybe you already covered log data inherently in this.
The closest I came to talking about that was where I said there's multiple sources of data. Log files. If you use something like Logstash, there are tools that allow you to create time series out of your incoming flow of log data. Log data being textual event data saying this occurred, that occurred. I mean, at the very basic level, HTTP hits in the response code and the response size, right? That's a perfectly valid data source, and sometimes you have to write the glue that converts it to a time series that's meaningful, or you only go and drill down into those time series when you know that when something else is detected there's an anomaly, and you use your log browsing dashboard to grep for things that are of interest. Like, for instance, I tend to, because I work for a company where most of our software is in-house, just about anything that will emit a log line will also increment a counter. If this was a more software engineering-oriented conference, I would have had a long rant about every time you log something, you need to be incrementing and exporting a counter because your operations people need to know that this particular error, the rate of which you're hitting, the DB connection timeout, is going up and up and up and up, and they don't want to have to grep and sum by the number of times that phrase appears in a log. But unfortunately, there are many apps that all they do is write that out to a log. Sometimes it's worth it to take the time to write something that post-processes that, either using a Ganglia or Logstash, which can do a stream-oriented creation of a time series, or you rely upon, all right, look, at this time, something started going weird, and I've been able to drill down and say it's something related to host AACD12. I'm now going to go to my log management system. I'm going to say, show me everything plus or minus 4 minutes on AACD12, and you eyeball it. And for many of our apps, that's as good as we need, because just about every one of those lines has generated an alert, and then we have another system which lets us say, okay, show me all the logs related to AACD12, or not AACD12. I want to see all the logs related to the process named foo running on any of my machines for that 2-minute window. And then that'll help me drill down and figure out the root cause. Does that help?
Yeah, thanks.
Thank you.
Hi.
Hi.
So I was wondering if you had any suggestions for tools for actually visualizing and using this data, because we log multidimensional data into OpenTSDB.
Great.
And we do some interesting things with it when we pull it back out, but it doesn't seem like there's actually good tools for pulling and sort of arbitrarily combining and excuse me, and summing data and whatnot. Are we missing something? Do you have suggestions for tools?
Yeah, I have a secret tool that I just haven't told anybody about. It's open source. Everybody uses it, and you're the only one not using it. No. The sad fact is, this is a moving problem. In the beginning, the problem was simply gathering the data. And so administrators feeling the pain wrote tools to gather the data. Now we're at the point that gathering and storing the data is the big, hairy problem. Meanwhile, visualizing is something that not a lot of administrators are great at. And so the best of the tools that are out there are things like Carbon. I'm sorry, Graphite. Yeah, Carbon's a storage layer, right? Who here uses Carbon? Should be a fairly large number, I think. Oh, only about a quarter. Carbon's one of the nicer visualization layers. It has its own problems with scale. If you go and watch the presentation I gave last year and flip through the slides, you'll see that, or who here got Tom Limoncelli's new book? Okay, a few. All right. I don't get anything for it, but he basically, chapters 16 and 17 are entirely cribbed from the LISA talk last year. He basically said this is the right way to look at monitoring, so you can either watch the talk and read the slides or read those 2 chapters of the book. And he does talk about visualization, because I categorize visualization as an open problem. In my formal model of monitoring, this thing here, who's seen this slide? Who's seen this talk either online or saw it last year? Only a few people. Oh, wow. Well, maybe I should offer to teach it again next year. In this here somewhere, this talks about the problem of monitoring in general. Here we go. These are the 7 fundamental problems of monitoring. If you want to do monitoring in any way, shape, or form, you have to address all 7 of these boxes, either explicitly or implicitly. All right? If you don't, you are going to be hurting in relation to one of those or the other. Now, the reason we came up with this formal model is because we saw that, like, why is it that Nagios doesn't quite get it done? Why is it that Sensu doesn't quite get it done? He's like, why do you always feel like monitoring is not a completely solved problem? And we sat down and thought, well, what would you have to do to completely solve monitoring? And we came up with this model. All right, now if you go watch the talk, I'll go into detail about what each of these boxes are, and then you'll see that up here, I have the exact same why do we monitor things. But in that talk, I talk about exactly where in the stack each of those things impacts the particular aspects of monitoring. And unfortunately, when it comes to operational response, all 7 parts matter and need to be solved completely. But if we go look at, skipping past the trivial ones, if we go look at things like Nagios and Ganglia and so on, they all focus on different aspects. Nothing focuses on all 7. Now, to a small degree, people are beginning to make solutions with interfaces that allow you to glue different parts together. We had our RRD tool for quite a while, right? Who uses RRD or has used our RRD tool? Everyone, yeah. What's the problem? What's the main problem with RRD tool and all the stuff I just said?
Dimensions.
What?
Dimensions.
Dimensions, exactly it. RRD tool stores one time series per file, and you end up, someone was telling me that they recently had a problem where their RRD-based backend, they had to go and increase the number of open file handles available so their Graphite UI would render because it was trying to open so many different RRD files simultaneously. The storage layer isn't optimized for an extremely high dimensional space. OpenTSDB does address that, but OpenTSDB only solves the storage layer problem. Doesn't solve configuration management, doesn't solve collection and so on. But you have things like Ganglia, whose main focus is configuration management, collection, and sensing, right? So all of us have glued together something that ends up looking like a variation of, where is it? And here's visualization solutions. Visualization solutions are often very standalone. D3 and Graphite are the two big ones. Graphite tries to combine a few other things beyond that. But real world, Nagios plus Graphite plus Sensu plus Logstash plus Ganglia, right? And that's because if you take a look at what each of the areas that each of those things solves, when you combine them, you now have a working solution. Nothing does all of it. And if you start with any one of them and you start with a checklist of those 7 things, say, okay, what does it do really well? You're going to know right away what things you're going to have to go and backfill. Unfortunately, the best visualization things out there right now is Carbon. You have to use Graphite. You have to use the what's the network Carbon backend? What? Is it Whisper? It's the Carbon backend for, there's the built-in Carbon and there's the query-based, API-based Carbon layer for Graphite. Well, anyway, when you're using Graphite, it can either directly go to the RRD files, or you can put an API in between, and there's a server that serves up the RRD files, caches them in memory, and does a bunch of things. You very quickly have to move to that. The problem is you're still on RRD files. I know of no way natively to glue Graphite onto OpenTSDB. I'm sure someone has already done that, but they just haven't, they've done it in-house. But right now, if I had to build it from scratch starting tomorrow, I would pick up OpenTSDB, pick up Graphite, and start trying to glue them together. Graphite, unfortunately, has some scaling issues with really large dashboards. I'm sorry? Graphite? Oh, Graphinet? Oh, Grafana. Okay, so he says Grafana can use OpenTSDB as a backend. Awesome. I've never used it, can't advise it, but if it plugs into OpenTSDB, then that might help you move along. And hopefully more people will start moving to OpenTSDB, which will cause pressure, and they'll start releasing contributions to the community that make our visualization tools better.
Thank you.
Oh, thank you. So somehow we've changed presentations. Yeah. And now I can't get back to the other one. Huh?
I heard of another one last night from another attendee here called Bosun. So
Osen?
Bosun, yeah.
Okay, so Osen?
Bosun.
Bosun. Oh, like
the guy
Bosun's
on a
mate.
boat in the old times that blew the pipe and tells everybody what to do. Yeah.
All right, blows the pipe, tells everybody what to do. Sounds like a good name for a monitoring system. Blows the pipe, tells everybody what to do. So that's good. Yeah, that's the hardest thing about this is finding somewhere somebody's got this working in a great way and they're not sharing it. You know who you are. We will find you. Anything else? Any thoughts, ideas, suggestions for your peers? Let me find a... As soon as I get approval, I'll share this with USENIX, and then it'll be up. There's nothing interesting there. We'll look at a puppy. So, yeah, I mean, there was a lot of info here. There are only 4 different kinds of numbers that are interesting. What kind of number you have affects how you can combine it. But you also need to have lots and lots of instances of those 4 different kinds of numbers. Right? Design your monitoring systems with intent. Think about why you're creating this number, not just because it's an exported counter. Think about what other counters it should be combined with. Yay, someone else talking.
Yay. Actually, I have a question about alerting. Having all this data with all these multi-dimensions is great for forensics, but looking at it as a pool of data to build alerts around so that you're finding out about when stuff's going wrong. Do you have any advice on how to do that with such a huge 3-dimensional grid of data?
Well, it's not 3-dimensional. It can be 10-dimensional or more, yeah. That is a very good question. Essentially, your alert rules end up being standing queries looking for thresholds, and they end up being aggregated queries. You know, some the average utilization of, some the usage of memory on a per process basis across, per process ID basis across the entire fleet, and look for the first derivative to change by more than, you know, X% per minute. And that indicates that one particular thread is spiking, and you alert on that. Now, those are the best kinds of alerts, because if your alerting language allows you to write those in a generic fashion, but then populate the page with the details that matched, then I can say, oh, by the way, on host AACD12, process foo thread 75 has spiked in its CPU utilization. Go look at it. And we are fortunate that we have some monitoring systems that do let us write rules like that. The syntax is mind-bendingly arcane, because writing generic queries over multidimensional data that's time series related, where you may have time series that are out of sync, it requires a syntax that, well, you need another dimension in your keyboard to write it. And so they approximate it with text. So yes, you do write your alerts in consideration of that, but the benefit is you also can get very, very targeted alerts. You know, very rarely do we alert on something as aggregate as CPU utilization high in the fleet. Instead, it's this particular process is beginning to run away in a way that differs from the others. And we also use self-aggregation. We say, you know what, I want to look at what the average utilization is for this kind of thing fleet-wide, and then pairwise compare the individual ones to the group and see is one of them behaving in a way that everything else isn't. Because if it's Wednesday, everybody's going to start trending up in their CPU utilization. What I care about are the ones that are different from the others. You know, that's a very meaningful thing. Also, the rate of disk consumption. I want to know if the speed at which this particular instance of my service is consuming disk is out of line with the rest of my service's disk consumption. And that can either be a baseline or it can be an absolute threshold. Sometimes we create separate capacity planning rules, like I want to know when my future disk space is going to run out in less than 3 months on any one of my machines in my fleet. But also when I want to know, in general, if my average utilization ever becomes more than X gigabytes per week, because that means I need to change how I provision data. I want to look at the first and second order derivatives of those values. And I have what are called capacity planning alerts that fire annually, that tell me that, by the way, the assumptions about how much CPU you need per active user is no longer what you thought it was. Very often developers like to push out new releases of software that changes the CPU load for particular usage patterns in a way that completely screws your capacity planning. And the only way to know that is to be able to take multiple metrics and combine them together. For instance, how many of you can say how many CPU seconds are consumed to service each active user each day? It's a very valuable number. Some of us can say it. You can say, oh, I know that I need, you know, for every 7-day active user, I need 40 core seconds a day and 6 gigabyte minutes of RAM, all right? And if that profile changes, then things are going to go different. People like to push software in the middle of the night. That's a terrible time to push software. Time to push software is in the middle of the day at the busiest time, because then if the active footprint, if the active behavior of your service has changed, you want to be able to roll it back when you're sitting there staring at it, not roll it out. Everything's fine when only 10% of your user load's in there, but when all of a sudden it starts trending up, instead of peaking out at 80% utilization midday, it's now peaking out at 100% utilization at 10 a.m. because somebody went and changed the memory usage patterns or the garbage collection patterns if you're dealing with Java. And so you want to know when that's happening right away. And the only way to do that is to route full production loads to canary machines as you roll out. So get out of the habit of rolling out at night and at low times. We roll out whenever. I mean, it's just automatic. It's midday. Doesn't matter what the utilization looks like. We just start rolling out. Because also, a machine failing for an upgrade, killing a machine because you're replacing it with a newer version of software, is indistinguishable from the machine failing because a cat crawled through the power lines, right? I mean, the things you do in those situations are the same. And if you can't handle the cat without interruption to your users, then you might want to look at that, because cats and upgrades should have just as much impact on your users. You know, and if a cat doesn't bring down your service or impact your users, then why not upgrade in the middle of the day? Because the upgrade Doesn't work, roll it back. Just the same. Take the whole cell offline, leave the load on the legacy one, roll back or roll forward with a patch. You know, get in the habit of releasing in the middle of the day. It's good. It's a good thing to get into. Because also then when your pager goes off, you're already at work. Or you're not sleeping in because you're at work till 3 in the morning doing the release. And then now at 9 a.m. on 5 hours sleep, all of a sudden you got to figure out what went wrong. So. Any other thoughts? Well, we'll finish early. Don't forget to do your evaluations and stuff. If you found this interesting, I'd like to know. Do email me with your thoughts. I don't recommend Twitter. Well, just because there's a rapper in Florida whose fans don't know his Twitter handle, and they think he's Caskey at Twitter, but he's not. He's Caskey407, but his fans don't know that. And every week I get hit up with offers to collaborate on records and play shows by promoters. And I don't, no. Mostly, what? I do. When they do, I say, oh, good idea, man. Sure thing. And then I just never hear back. But presumably the other guy's getting weird calls. You know, it's like, what do you mean?
Thank you for presenting.